The Ukrainian AI community used to create, develop, and educate for a shining future. But then Russia ruined our peace. We switched to a new reality. We do our best to defend our country. The brightest AI minds came to share knowledge with us. Together, we will build a technological and secure future. Peace in Ukraine equals peace in the world. Support Ukraine. Support the AI community.
Hello everyone. Welcome to AI for Ukraine, a series of workshops and lectures by international AI experts to support the Ukraine's tech community during the war. We apologize for the delay. We had some technical issues, but now everything works perfectly, and we are happy to welcome you on our live stream. Thank you for joining us today, and of course for supporting Ukrainian army with your donations. We have already collected more than 200,000 hryvnias, which we will transfer to the biggest Ukrainian foundation, Come Back Alive. My name is Hanna Shuvalova. I am a CEO and managing partner of Power, an ML-focused venture studio. Power is a part of Frush ecosystem and is as AI House, a Ukrainian AI community that made today's event possible. Today, we have an amazing speaker, a world-leading researcher in AI and the pioneer of deep learning, Professor Yoshua Bengio. A few years ago, his groundbreaking research in deep learning was recognized with the Turing Award, known as the Nobel Prize for Computing. And as of now, he is the most cited AI researcher in the world. Today, Professor Bengio will speak about how we can bridge the gap between current deep learning and human cognitive abilities. In a few minutes, our guest will appear on the screen, but first, let's figure out some housekeeping questions. The tool we will use to submit questions during the live stream is called Slido. Please open slido.com website, slido.com, in your browser and put AI for Ukraine code, your name and email. Or you simply can click the link under the video. So let's check how it works together. Now I will start a poll, and in the poll section, please type in the name of the city where you are currently located. Meanwhile, I invite Professor Yoshua Bengio to the studio.
Hello.
Hello, Professor. How are you doing?
Great, thank you.
Thank you so much for joining us today. We have a lot of people watching us now. Now, on your screen, you can see that we have viewers from not only from Ukraine, but from other cities and countries around the world. As you know, a lot of Ukrainians had to relocate during the war, and we really are happy that people from different countries and different cities are able to join us and see your talk today.
It's my pleasure to be able to address you today.
So, as you see, the biggest portion of our viewers are currently in Kiev and Lviv. We also have guests from Tbilisi, Berlin, Lisbon, and many smaller Ukrainian and European cities. By the way, Professor Bengio, where are you now?
Montreal.
Oh, awesome. So it must be quite early there.
It's okay.
Okay, thank you guys for participation. Going forward, we will be using the same tool for your questions. Please feel free to submit those as you watch the lecture. And I'm passing the word to Professor Bengio.
Can you share the screen? Yes, great. Thank you. So I'm going to tell you about my current research program, which, as the title says, is about trying to bridge the gap between current state-of-the-art in AI based on deep learning and human intelligence, in particular, focusing on high-level cognitive abilities. and I explain why we think it's important. So current machine learning suffers from serious robustness issues, especially when you deploy the systems in settings um, which we call out of distribution, meaning a different distribution from the training distribution. And unfortunately, even if you had very large data sets for training, if your setting of application turns out to be somewhat different distribution, then you can have a fairly bad reduction in performance. So this raises all kinds of interesting research questions. For example, we used to rely on the IID hypothesis that the test distribution is the same as the training distribution. But if we don't have that assumption, we need some alternative assumptions. Otherwise, why would we expect any kind of generalization? And more precisely, we need to think about how distributions can change. How come humans are able to handle these situations so well? What kind of inspiration can we get from the way humans do it? In particular, how, what evolution has put in our brains that allow us to do this. And this raises interesting question when you think about changes in distribution. Of course, some things have changed, but also some things have remained the same. And that must be some kind of general knowledge. So this is the question of knowledge representation and how humans do it, as well as how future AI might be doing it. Okay, so this is related to a question that linguists have been studying for many years called systematic generalization, which you see in natural language. You can take words corresponding to concepts you're familiar with and arrange them in a completely novel way that not only you've never seen, but maybe would be very unlikely, and you can still understand what it means. Like in the picture here, I mean, it's not words, it's images, but it's the same principle of systematic generalization. So humans are really good at that kind of generalization, even to configurations that would have zero probability under the training distribution. For example, we can take what we know about driving in our home country and kind of generalize to other countries where maybe the traffic laws are different. So yeah, there's a lot of papers showing that current approaches are not that great at doing that. And it's interesting to see that humans are able to do these things. So to summarize the nature of the gap between state-of-the-art AI systems and human-level intelligence, there are a number of points that are all kind of interrelated, actually, and I'll talk about in my presentation. One is what's called sample complexity. In other words, how many examples do you need to learn a new task sufficiently well? And currently, there's a huge gap. So, we have these amazing large language models, for example, but they require amount of data that would be many thousands of lives of a human being, right? It doesn't make any sense. So we're missing something qualitative. Just scaling up is not going to be sufficient. And of course, there's this question of how these systems can generalize to new settings out of distribution generalization, how fast they can adapt in new settings. So that's like transfer learning. So it's the same question of sample complexity, but in a transfer setting. And it turns out that these questions are related to the abilities of humans to make causal connections, to discover causal connections, and to reason about these concepts, meaning they can make inferences in fairly novel ways, but combining the pieces of knowledge they already know. So this also raises the question I mentioned of how knowledge itself is represented, and it has to be represented in a compositional way, something we see in natural language. So humans clearly have a way to represent knowledge that have those properties that allow to recombine the pieces and do new inference very efficiently. So we need all of these things in future generation of AI. All right. So there's a clue that all of the things I've talked about are related in humans to one thing we don't know how to do well in current AI, which basically has to do with conscious processing. When your brain is processing information that becomes accessible consciously, it's actually doing things quite differently. And neuroscience has been teaching us a lot about how that is going on in your brain. So unconscious processing and conscious processing is actually quite different. And and we may learn about how to build AI that have these abilities if we better understand the neuroscience of conscious processing. Okay, so let's go a little bit more detail about this. I'm going to take the example of driving that I talked about earlier. So what happens when you are in a new situation, so out of distribution? For example, the driving example, like you've been driving in a country where you drive on the right side of the road, and suddenly you rent a car in a country where you drive on the left side, like UK. So what's happening there is that you can't go by your habit. If you do that, you're going to make an accident. Your habits are going to not your impulse to how to react to things is just wrong. And what happens in those situations is we concentrate, we pay attention, we keep reminding ourselves that, oh, I have to drive on the right. So this is calling upon the notions that are starting to come up in neural nets, like attention, but we're still missing a lot of pieces, like this knowledge representation aspect. We can take kind of factor pieces of knowledge, like everything we know about driving can be factored from the fact that we should drive on the left or factored on the right, or drive on the right, right? So there's somehow we have this ability, but it requires this special kind of processing, which is different from the habitual processing. And psychologists for many decades have been studying this dichotomy between two different styles of processing, two different styles of cognition in the brain. And one nice way to make that distinction is called system 1 and system 2. So the system 1 is the intuition, everything that you can do very quickly without thinking in a habitual way. And it happens at an unconscious level. You don't need to pay attention. It's hard to explain in words what you're doing. You're using some kind of implicit knowledge. And current deep learning is really good at that kind of thing. But what we need is now consider system 2 abilities, also neural nets, but of a different kind somehow, or maybe organized in a different way or trained in a different way, we don't know. And that corresponds to what you do when you have these new traffic laws and you have to think and reason and pay attention. So it's slower, right? If you stay in that country where people drive on the left for enough time to practice, then eventually it will become quick. But initially, it's going to be very slow. You can't drive very fast, for example, in London in the first few days that you're there. You're very conscious of what you're doing. You can explain to people, okay, I'm paying attention to stay on the right. This is actually similar to the process by which we come up with things like algorithms and that we can plan in ways that we can explain to other people. And of course, it's highly related to the notion of reasoning, at least the way that humans do reason. Okay, so let's consider in particular this question of knowledge representation I've been talking about. In order to transfer knowledge from an old setting, like a training distribution, to a new setting, which has a different test distribution, somehow we need to be able to organize the knowledge in a way that the pieces that can be reused from the training distribution can be easily extracted and composed in order to solve the new problem. And this is not something that current deep learning architecture can do. At least it's not clear how they would do this because we have these large homogeneous architectures where knowledge is not localized. But if you look in your brain, knowledge seems to be highly localized. Like if we peak in one place, we see these neurons are doing this thing, and another place, these neurons are doing this thing, and so on. So there seems to be a lot of specialization in the brain that is not necessarily obvious in our current deep learning. And this is, of course, important to solve the tasks I was talking about. All right. So let's take now a physics perspective on this. Think about pictures that you take on the Earth, like typical pictures you find on the internet, versus pictures you might take if you're on the moon. It's a different distribution, obviously, And yet human beings have no trouble understanding the pictures we get from the moon. I mean, maybe it's surprising, but we understand them. So what is going on here? Well, what is it that allows us to generalize? One way to think about this is there are really two kind of ingredients that explain what we're seeing. One is, think of it like the laws of physics. The world evolves according to some laws, some rules. There's a dynamical system that differential equations and so on. But it also depends on a second ingredient, which you can think of initial conditions or the current state. So things on the moon look different because it's the same laws of physics, but the conditions are different. There's no atmosphere and there's no life and so on. And so we observe different things, right? So there's this notion of breaking down knowledge about the world into the parts that are stable, like the laws of physics, and the parts that can change if you go from one place to another place or one time to another time. And that's different from the regular IID assumption, where we assume that everything is the same. We're going to assume that the things that are the same, that are preserved across distributions, are like the laws of physics, the dynamics and so on, the causal structure. But the things that can change are these state variables, these conditions, right? So there's a notion that's been proposed already for about a decade called independent causal mechanisms, which may help us think about this question of separating knowledge into the stable pieces and the things that can change. And one way to think about how we should be organizing knowledge into pieces that can be reused easily is to think about how we write code. So the way that we write code is we try at least to factorize the required computation into independent pieces of code. So what does it mean, independent pieces of code? Well, it means that if I have to change one of the pieces of code, one function, one module, I don't need to change the others, ideally, right? So the best way to factorize code is would have this property. And mathematically, this actually corresponds to a clear definition that has to do with sort of the information. There should be as little mutual information between different pieces of code, meaning that if I take two functions in my code, taken like randomly, if I compress them with zip, say, separately, or if I compress them together, I should get the same length. So there's no information about each other in those pieces of code. So we'd like that kind of factorization. So this is actually a concept that comes from theories of causality. And causality is something I'm going to talk more about. It's something that we are missing in current deep learning, but actually it was something from the early days, when we were starting to work on deep learning and thinking about higher level representations. If we were working on unsupervised learning, like with Boltzmann machines and so on, and we were thinking, well, we'd like the high level representations to represent the explanatory factors, which are like causal factors. But how do we discover them, especially in an unsupervised way? Of course, we can use supervised learning where we say, okay, there's labeled data. These are the factors. These are examples of values of these factors. But the hard part is having a machine that can discover these things, and also not just discover the factors, the high-level variables, but also how they're related. And that's the causal structure. So there's some abstract concepts which are removed from the pixel level, like objects and actions, and not only we need to extract these things from the raw data like images, but also we want to model how they're causally related. Like if I drop a ball, it will fall. So maybe through not just a single image, but think of a sequence of images. And that's connected to reinforcement learning, of course, because those changes have to do with cause-effect relationships and how our actions will produce some outcomes. Okay, there's another important viewpoint here that can help us sort of build this future AI, which is looking at the way humans represent information about the world in a kind of with language. And we can look at language. It gives us a lot of information. So but not everything in our brain is something we can verbalize, that we can explain. In fact, the majority probably of things we know are not verbalizable, and so they belong more to system 1 that I was talking about, whereas the kind of knowledge that is verbalizable is system 2. So maybe there's a good reason for having these two kinds of these two types of knowledge. So if we look at language, I will argue that we see that system 2 knowledge obeys some inductive biases. It's some sort of soft constraints, and if we understand these inductive biases, these preferences, and how to design the joint distribution basically about these concepts, we should incorporate that in AI, at least for representing the system 2 level information. So one of these inductive biases, the one that I've written the most about, is the assumption that the high-level concepts, so think about what we name in language, like if I say, if I drop the ball, it will fall on the ground, you have concepts like the ball of dropping and the agent me doing the action. So what's interesting about these concepts that we manipulate with language, if you think about them from a statistical or causal perspective, is that the dependencies between them are very sparse. A single sentence, like if I drop the ball, it will fall on the ground, that includes very few words, allows me to make a prediction about a variable, one of these high-level variables, like the position of the ball, and the prediction is very accurate, and yet it relies on very few variables. This would not work if you try to do this at the level of pixels. Like, in other words, if I try to predict one pixel given 3 or 4 other pixels, it will not be a very accurate prediction. But if I do it at the level of these named entities like balls and ground and so on, it works. So somehow these named entities have a kind of statistical structure that is different from pixels. And we need to incorporate that kind of inductive bias. And in addition, many of these words refer to causal structure. So think about the relationship between the ball position before and after and my action of dropping, right? There's a causal relationship here. So the things we name with language often play the role of cause, effect, agent, the entity that is doing the action, the intervention, and the actions themselves, right? Which are what mediates the relationship between cause and effect. Also, a very, very important property of these high-level entities that we'd like our neural nets to model is that the relationships, the causal mechanisms, the links between those entities, they are abstract themselves. They can be reused. So the same verb dropping can be applied to me dropping the ball or me dropping the phone. So there's this reuse of components here that's very important, and it's not obvious that we don't have that for free in current neural nets. But I'll talk about ways using attention to bring in that sort of reusability. Another characteristic of these verbalizable concepts is that for the most part they're discrete. We use words, so they're symbolic. And so that's interesting because of course lots of what we've done with neural nets is all about continuous stuff, and then that's has a lot of advantages. So how do we mesh these things together? One idea that I have is that connects these two things together is that what's going on when you're becoming conscious of something is that the brain dynamics is converging to some attractors. And the number of possible attractors is not a continuous quantity, it's a discrete quantity. You can either fall to one attractor or another attractor. And so these attractors are the discrete entities, right? So, but of course, where these attractors are is a pattern of activation of neurons in the brain. It could be a continuous quantity. So it's like word embeddings in current deep learning. there's an enumerable set of word embeddings corresponding to different words. They're discrete, but they also associated with a continuous quantity, which is this representation. What we found in recent work is that if we introduce this kind of discretization in neural nets, in the communication between different modules of a large neural net, we actually get improvements in out-of-distribution generalization. And the intuition here is that the different parts of the brain, say the different modules in the neural net, can now talk to each other through this language of discrete choices that makes it easier to hot swap one module for another module communicating together. And so, for example, in language, we can replace a noun by another in the same sentence. Okay. Another inductive bias has to do with the action side, like reinforcement learning. When we think about what has caused changes in the world, we can typically boil it down to a single entity, a single action, a single cause. Somebody's done something, and we explain this with a sentence. So this is actually also a very strong, very, very strong assumption. And sometimes it's wrong, of course, but humans tend to make that assumption, and we should incorporate that in our models. So we've started working along those lines. These are some of the papers that show that incorporating these kinds of inductive biases helps to obtain better out-of-distribution generalization. So these were like recent papers at ICLR and NeurIPS. And so now, what's next? What are we missing? Well, up to now, we've kind of stayed with those papers in the realm of standard, differentiable neural net systems. But I mentioned, that these discrete things, and if you go into the neuroscience, it looks like there's also a randomness aspect. So think about the Necker cube. Think about the fact that in the same situation, you might think with one thought or another thought. This seems to be a little bit random, and different people will come up with different explanations. So there's a stochastic aspect. The discrete stochastic aspect is something that we haven't incorporated, and that's related to our ability to imagine things. So maybe we need some sort of generative neural net to generate thoughts from a distribution. And there's a way to think about this from a machine learning and probabilistic point of view as a Bayesian posterior that we are sampling from. So what is the explanation for what I'm seeing? And it seems like our brain is doing that sort of thing. So we need neural nets that can do that. So recently, motivated by many of these elements, we've introduced a new kind of neural net architecture. Well, it's not really the architecture, it's more how we train it, which we call GFlowNets for generative flow networks. That is a fairly general purpose probabilistic modeling tool. So I call it the Swiss Army knife of probabilistic modeling. And what it allows to do is to model distributions over composed objects, which is really what we need here. Like most of deep learning has been focusing on vectors. Okay, so we have vectors in input, we have vectors in the hidden layers, we have vectors in output, and that's served us well. But now, when we start thinking about higher level cognition, we have these thoughts, these sentences. They are compositional. They have a structure. And a good way to think about that structure in an abstract way is as a graph or a hypergraph. And the way that thoughts come to us is sequentially, where the little pieces of thought are getting composed one after the other. So these GFlowNets are a little bit like this. They generate composed objects like graphs by sampling one element at a time, given the previously sampled elements. And they learn a generative policy that can sample these objects according to some reward function or some energy function that can also be learned. There's also an interesting notion which gives the name to the method of flows that I won't have time to go into detail, but basically these the math for these GFlowNets also allow us to do what is called marginalization, meaning compute quantities that correspond to intractable sums. And of course, it will be estimators of these quantities, like the normalizing constant or conditional probabilities that are normally very difficult to compute, but these neural nets can estimate those quantities. All right, so if you want to learn more, there is a tutorial that I have written, which I think you could find easily if you type GFlowNet tutorial in Google. There's a tiny URL here, GFlowNet tutorial, and it includes links to about 6 papers that have come out in the last year about this approach. Let me try to explain a little bit more how these GFlowNets are generating these structured objects like graphs. So first of all, we're going to be using existing techniques for handling graphs. Graph neural nets have been around now for a few years, and they're an amazing tool. But what they do is they generalize the notion of deep learning to take as input something like a graph rather than something like a fixed size vector or a sequence. And so how are we going to use this to generate graphs, right? So now we want to produce a graph as output. So we're going to do it sequentially in a way that imitates a little bit with what we think happens with thoughts. So we're going to construct something like a graph, a compositional structure, by adding one element at a time. So at each step, we take as input, using a graph neural net, the current partial graph, I mean the partially constructed thought, and we're going to output a distribution, like a policy, over all the possible actions, like add an edge. So each of the outputs may represent a potential action. And we're going to sample one of these actions, which correspond to, say, adding a node or adding an edge. And that is going to give us a new graph. And now that becomes the input for the next step, and so on. So we're going to train that policy with an objective that has to do with, how good is the graph? Like, what kind of reward do we get if we use this graph? So GFlowNets are really part of reinforcement learning, but they also have fairly different properties. Also, those GFlowNets can be organized in modular ways. So instead of thinking of this like one big homogeneous graph neural net that does everything, all the actions, for each type of action corresponding to specialized types of knowledge, we can have a different module that's going to output not the probability, but a sort of an unnormalized probability for this action. And then we're going to use an attention mechanism to, just like we see in the brain when you're becoming conscious of something, there's a competition between different parts of the brain, different content that's going to win the competition. And then that content is going to become available to all the modules in your brain. There's a broadcast process going on in your brain when you're becoming conscious of something. That something has been competing with other potential contents. And so we can imitate that sort of architecture, which is called the global workspace theory in neuroscience. Yeah, so this is sort of a picture that illustrates that sort of thing. You see, instead of having this one big neural net I was talking about, you have different modules. And these different modules are now specialized to different types of knowledge. And they output an unnormalized score, like an attention, unnormalized attention score. And that says, oh, I have a piece of content that I would like to share with everyone. And then there's an attention mechanism that makes these compete with each other. And then one of them is selected stochastically. This corresponds in the brain to what's called the ignition process of conscious processing, where one piece of content is selected and sort of shared across the whole cortex. But these modules can also be connected to each other in a more standard way. So they may receive inputs from the outside or from other modules. What the green part, the conscious part, the competitive part does is it allows these modules, any of these modules, to to share content information with all of the other modules, because the thing that is selected, that's the blue links, is shared to all the modules, and this is called working memory. So working memory is something that's been studied in cognitive neuroscience for many decades, and it contains the last few items that you've been thinking about. So it's the content of your recent thoughts, and every module gets to see the last bit that's been added. At least that's the model that we are thinking about. You can also have a long-term memory, episodic memory, and in fact, that's an interesting neuroscience fact, which is only the contents that you became conscious of that go through your working memory can go to long-term memory, can go to episodic memory, memories of thoughts you had in the past. Basically, anything that didn't get to cross the threshold of consciousness doesn't get stored in long-term memory. Okay, the last couple of things I want to mention have to do with back to causality now. So this is there's a whole field of research outside machine learning, but more and more inside machine learning, to try to think about how we can model causal structure, how we can discover it. And one of the hard questions when you think about causality is that the same data that we may observe about relationships, about which configurations of the causal variables we can occur, can be interpreted in several ways in terms of the causal structure. So, if I observe two variables A and B, and they're correlated, I don't know if A causes B or B causes A. Even if I had infinite amount of data, I couldn't say. So this is the problem of identifiability. And it's like, causal knowledge is somewhat different than usual statistical knowledge. So what is the difference? The difference is that causal knowledge also tells us how that relationship could change if somebody, an agent, were to do intervention. Like if I change A unconditionally, it's going to maybe have an effect on B if A is a cause of B. But if it's B that it's the cause of A, then changing A will not change B. So if I open my umbrella, it's not going to make the rain come, right? But of course, if somebody makes the rain come over me, I will probably open my umbrella. So the causal connection is asymmetric, and in general, given some data and given maybe even knowledge of intervention. So if you knew that somebody intervened and modified A, then you can discover the causal relationship. But usually we don't have all the interventions. We don't have infinite amount of data. So there will remain some ambiguity about what is the true causal structure. And if we want to avoid making like really stupid mistakes in the world, we need to somehow account for that ambiguity. If a drug is really the cause of curing people versus people are cured for a different reason, this is very important information for saving people's lives. So understanding the causal structure is very important. But if we make the wrong, if we assume a particular causal structure that fits the data, so it's consistent with the data, but it's the wrong one, we can make really bad mistakes. So the solution is somehow to build models that can capture the whole set of possible causal explanations. And it looks like humans are able to do that, and to sample, like to generate one of these causal hypotheses, and then maybe the next day a different one. Right. So we need mathematically, the way to express this is say that we need the Bayesian posterior over causal models. And and there's an extra complication, which is that we don't actually observe these causal variables. We get pixels and we get low-level actions. So we also need to learn the relationship between the causal variables that are like latent variables, hidden variables, and the things that we actually do, the interventions, and the things we actually observe, like videos or sounds. So we have been using these GFlowNets to learn how to sample and represent this Bayesian posterior over causal graphs or probabilistic graphs. So this was just presented last week at the UAI conference. And this is work led by Tristan Deleu. To make things a little bit more complicated, especially if you're interested in reinforcement learning, and interventions are abstract. So if I say I'm going to drop the ball, this is an abstract thing. What I actually do is move my muscles. So there are low-level actions, and they may correspond to some high-level intention. So maybe I want to drop the ball, and maybe I'm not able to do it perfectly. Well, hopefully I can, but if I'm trying to push the ball, maybe I don't manage because there are some obstacles. So there's a distinction between a sequence of low-level actions that have the aim to achieve some intervention, like pushing this ball around, and actually achieving it. So this connects to lots of literature in reinforcement learning. There's a notion of options and higher level hierarchical reinforcement learning. And the idea is that you may have a high level policy, which is about those high level concepts. And then there are skills or low level policies that convert these intentions to achieve some objective at the high level into sequences of low level actions. Right. Okay, so I'll stop here, and I hope this was interesting, and be very happy to answer questions now.
Thank you, Professor Bengio. It was really insightful talk, and we will make sure to share the links to the resources and the papers you mentioned with our webinar participants. We have quite a lot of questions from the audience, and we know that you are tight on time, but we hope that you will be able to take at least a couple of those. So the most popular question comes from Bogdan. Do you believe in achieving AGI based on silicon computing materials, or should we figure out more biological way of computation, like similar to human brain?
Yeah, this is an interesting question. I do believe that we can get an understanding of the high-level principles of intelligence from how brains work, and by playing with different AI algorithms, and that would be sort of abstract, and it wouldn't depend on the implementation. I don't believe that the low-level details of how it's done in the brain matter that much, except for efficiency, and scaling. So if we want to build machines that have the same sort of compute power as the brain, we may need to go to analog computing, for example, to have energy efficient computation.
Thank you. And the next question also comes from Bogdan, but another Bogdan. So do you think traditions which have full-on studied aspects of consciousness, for example, Buddhism, can help to deepen our understanding of AGI and approach to AI models?
That's an interesting question. Well, it can't hurt. So I've been a big reader of philosophy and also of Buddhist writings, and so I think our ability to what's called metacognition, our ability to step back from our train of thoughts, which is something like Buddhists study quite a bit, is a key ingredient in our conscious abilities. So I don't know at what level we can, take advantage of what Buddhists have found over the centuries, but clearly this is an aspect that we would like to have in machines, and this is for very practical reasons. We want a machine that's able, when it's confronted with somewhat of an unusual situation, to think back and like even consider the bigger moral picture of its actions. This is important for our own survival, I think. So I would say, yes, we should be open to a discussion with philosophers in general about consciousness. It's quite important.
Thank you. And another question. Can we think about independent pieces of, I'm sorry, maybe some insight or your vision of possible future links from fully computational AI to something unexpected in the field of pure math?
Well, I'm not a pure mathematician, but I think math is very important in machine learning. If you look at the work we've done with GFlowNets, there's a paper called the Foundations of GFlowNets, which I don't think that it innovates in math, but it relies a lot on things like measure theory, and I think that some of the progress we need to do in machine learning can really benefit from people that have a very strong math background. I don't know if that will innovate on the pure math, but clearly it can be a very important ingredient to understand the more abstract, some of that more abstract questions that we're trying to deal with.
Thank you. And another question. I see that we have one question asked 2 times, and it's about GFlowNets. So what is still missing? What are the next steps?
Right. Well, we developed GFlowNets for compositional discrete objects like graphs. And one of the interesting questions that we're starting to look at, but I think deserves a lot more attention, is how to generalize them to continuous valued objects. So, small continuous vectors is pretty easy. You can just do sequentially one element at a time. But large continuous vectors is more interesting, and we have some ideas to do that. But I think that's one example. Another area that's interesting is how to train them properly. So several of the papers we've been working on recently have to do with that question. So in the original paper, we had an algorithm that was inspired by reinforcement learning, Bellman equation, and so the bootstrap process. It turns out you can do much better with different algorithms, and I think we're just like scratching the surface. And then one area that I'm very interested in is how we could use GFlowNets to implement some of these system 2 inductive biases, and they could be used for things like coming up with a Bayesian posterior over theories that explain data at a symbolic level, for example, which is something that humans are very good at. So you can think of these like neural nets that manipulate symbolic structures and can discover or like figure them out from data. I think there's a lot of potential to explore there as well.
I see there is a lot of interest from the audience in joining your research. Is it possible? And if so, then how?
Well, I work at MILA. This is an AI institute that is funded by the Canadian and Quebec government in Montreal. And there's like 60 professors. There's something like 600 or 700 students. So it's a very large institute for machine learning, and every year we recruit people from all over the world for PhDs, postdocs, masters. There is a process for trying to be matched with one of the MILA professors that starts in the fall, usually around mid-October, and you have until like mid-December typically to apply. This is just to try to kind of connect the right people together. I mean, professors with students, and then you still have to apply to the universities. My group is very large. I'm trying to reduce it, but I'm looking for people who are interested in these questions and also applications of these things in drug discovery, something I started working because of the pandemic, in particular for areas of biology where current industry is not doing anything, but is quite important. for the survival of humanity, like the next pandemics. Please, just reach out by email.
Thank you. I'm sure you will see an inflow of applications from the Eastern Europe and Ukraine in particular very soon. So I see that we have probably the time only for the last question, and we somehow missed one of the most popular questions, which is it fair to say that we are moving or should be moving from architecture-driven, data-driven deep learning towards a novel causality-driven approach?
Yes, but the causality-driven approach is also data-driven, right? So it's just that what you extract from the data and also from interacting with the environment, so that's the action part. So RL is now going to be a big part of this, is a causal structure. So you want to have machines that can, like children, 4-year-olds, they play with some toys and there's a causal structure there and they discover it. And they don't just discover it passively, they explore in a smart way. So they do experiments to try to figure out, is A causing B or B causing A? So this is exactly what we need for the next stage. It's related to everything I've been talking about today. So this is something that people in machine learning are becoming interested in. There was I co-organized with others several workshops over the last few months. And I think there will be much more of that community is going to grow in the coming years.
Thank you, Professor. Thank you for your time, for the lecture, and for answering our questions. We wish you all the best and hope to see more groundbreaking research coming out of Mila. And of course, looking forward to seeing Ukrainians on your team at some time in the future.
Actually, I have one Ukrainian in my team already.
Oh, really?
And I want to say that, I also wish the best for Ukraine. Peace is the most important thing we need for science. And to the AI community in Ukraine and around the world. So thanks for having invited me. Bye-bye.
Thank you. Goodbye. Okay, guys, I hope you liked this session as much as I did. And you are looking forward to the next session that will be coming with the support of AI House starting the next week. So next week, we have a practical workshop with Alex Mala, distinguished scientist and VP at Amazon Web Services. To help AI House team, I would like to run a small poll to understand some of the topics you are interested in hearing about in the future. So please help us to determine the themes for the next sessions. Thank you for your active participation and see you next week.